Okay, so this is the second lecture for our class, and so remember that last time we spent most of the lecture introducing the basic terminology and notation associated with partial differential equations, and also talked a little bit about some basic but important examples of partial differential equations, which we'll be encountering throughout the semester. And so, right, so remember when we left off, I was just beginning to introduce the first type of kind of general equation that we're going to develop a method to solve. And so these are this type of equation we're going to focus on for the first part of the lecture are equations that are called first order linear partial differential equations, or PDEs. Right, and so we encountered this terminology last time. So remember that first order means that it's just it may involve partial derivatives with respect to different variables, but they're all only first order derivatives. There's no second derivatives involved. And linear, remember, means that if you think about this in terms of the differential operator approach that we introduced, that this differential operator that describes the equation is linear. More intuitively, what does it mean? It means that if you have two solutions and you add two solutions together, you get another solution, basically. This is this superposition principle. And so we're going to look at equations in particular, equations of the form, well, I'll have a partial derivative of u with respect to x, right? And so again, we're going to be working with a function u of two variables. There are ways to think about this for functions of three variables or more, but you get sort of the main point just by focusing on the two variable case, right? So there's going to be some component involving the x derivative of u and also the derivative of u with respect to y. Sorry, let me make some more room. And they're going to be set equal to 0. But we're also going to allow for certain coefficients in front of these derivatives. And in particular, I'm going to be allowed to multiply ux by some function a, which could depend on x and y, and multiply uy by some function b, which can also depend on x and y. And so these two coefficients, again, which are functions, these are going to be given to you. Right, so the problem will be given some function a and b, can you solve this equation, which I just wrote out, which is this first order linear combination of u sub x and u sub y, or of the x and y derivatives of u. And so, right, so it's going to turn out that there's, which is actually pretty rare for the study of partial differential equations, it's going to show out that there's a general method we can develop which will tell you always how to solve these particular PDEs. Of course, you're going to need some kind of initial condition in order to get an actual function as an answer, and maybe we'll talk more about that later on. But still, this is one of the rare examples where you have like a general machine to solve these types of problems, which is what we're going to talk about first. And so, as is standard in math, what you really want to do to understand a problem like this is first look at the simplest possible version of the problem that still captures a lot of what's going on. And so in study of differential equations, the way to do this is usually to assume that all the coefficients are constants, right? So we're gonna first assume that these functions a and b are constants, meaning they don't depend on the variables x and y. And so this is usually called the constant coefficient case. As opposed to the variable coefficient case where the functions a and b can depend on x and y in complicated ways. Right, and so in the constant coefficient case, the PDE we're going to look at is just, well, I have a times ux plus b times uy. Is equal to 0. and A and B are some constants that are given to us. Right, so for example, maybe like say 3 times ux plus 2 times uy is equal to 0, right? So this a partial differential equation that looks something like this is a typical example of this type of problem. Right, and so now what we're going to do is talk about how do you solve this. And so I said a little bit, I gave a little bit of an indication of the method that we're going to use at the end of the previous lecture. And so, right, so what I'll do now is review what we said and then go into a little bit more detail and actually tell you what the solution is. Okay, and so the important observation, which is a geometric observation, which we'll be able to use to solve the problem, or at least by solve the problem, I mean determine what kind of functions solve our solutions to PDEs of this form. Well, the important observation is that I can rewrite the equation in vector form by viewing it as a dot product of 2 different vectors, right? So notice that if I look at the left-hand side of my equation, which is a times ux plus b times uy, I can write this as the dot product of the vector where I have a and b in the first component times the vector where I have the first derivative of, or sorry, the derivative of u with respect to x in the first component and the derivative of u with respect to y in the second component, right? And so if you remember back from multivariable calculus, this has this is a special and important type of object, which is called the directional derivative, right? So if I rewrite this, I can write this as the vector AB, which remember is always given to us. For example, it may be 3, 2, if you look at the simple example above, dot product with the gradient of u, right? Because the gradient of u is exactly this vector that has the first partial derivative in the first component, and then the second partial derivative, or the partial derivative with respect to the second variable in the second component. And so what does our PDE say, right? So the PDE says that, again, this is just a matter of notation. I'm just rewriting it in maybe a hopefully more familiar or insightful way. It says that if I take the dot product of the gradient of my function with the vector a comma b, that this has to equal 0, right? And so now it's worth pointing out that the quantity on the left is, right, a comma b dot product gradient of u. This is the directional derivative of u in the direction a comma b, right? So in particular, this means that this quantity, right, so if let's say I pick a particular point, let's say this is my point x comma y, and let's say this is right, let's say a comma b is over here, right? So this is the point we were given. Well, if I move my function, let's say I'm at this point x comma y, and I move my function in the direction a comma b, given by the vector a comma b, this quantity measures how much my function, the rate of change in that particular direction, right? So it measures the rate of change in the direction a comma b. And so once you make this connection to directional derivatives, well, this partial differential equation has a nice geometric interpretation. And what it's basically saying is that at any point, if I move in the direction a comma b, my function has to remain constant, right? Because the derivative is 0, meaning that the values can't change if I move in the direction a comma b, right? And so the consequence is that the solution u cannot change or must remain constant along any direction, or along the direction A comma B. Right. And so we're going to use this observation to determine what the solution has to look like. And actually, one thing that's worth pointing out is, before we move on, let's just go back to the above partial differential equation. Right, so notice that since I have 0 on the right-hand side, I can also multiply the left-hand side by -1, and I have the same, right, the equation will still be valid, just with like a minus sign on the left-hand side, for example. So it's also true that if you move in the opposite direction, exactly opposite, like minus A comma B, that the same property is going to hold. So I can actually say plus or minus. And so this is going to be relevant for what we're about to look at. Okay, so what does it mean geometrically that the solution can change along the direction A comma B, or along the direction minus A comma B? Well, this means that if I pick a particular point and I move in a line through that point with the given direction, the solution can change, right? So let's draw a complete picture, right? So this is my X and Y axis, and let's say this is my point X comma Y. And let's say I draw a line L with slope B over A that goes through the point X comma Y, right? And so if I draw that line, maybe that line's going to look something like this. So this is my line L. Right, so remember, why did I pick B over A as the slope? Well, remember, the slope is the change in Y over change in X. The change in the Y component over the change in the X component. Well, if I'm moving in direction A comma B, then, well, my Y component is changing by, my Y component is changing by some multiple of B, and my X component is changing by some multiple of A, which will cancel out. So the slope is going to be B over A, right? It's going to be this ratio, which you can also think of as like the dy dx. If you're thinking about this in terms of derivatives, right? The slope is the derivative. Right, and so if I have a line that moves through a fixed point, say X comma Y, and the slope of the line is B over A, then it's going to be moving in the direction A comma B, right? And another way of thinking about this is if, well, let's say this is my point A comma B, which is given to me. Well, the vector A comma B looks something like this, and so the line is just going to be parallel to the line is going to be parallel to this vector, and so in particular, the slope of the line has to be the same as the ratio B over A, or the slope of this vector, right? Right, and so, well, what is this consequence I have starred above this? Well, this means that if I fix my point X comma Y, as I move X and Y along this particular line, my function U can't change, right? So U of X comma Y has same value at every point on the line L, right? And so the more compact way of saying this is that U is constant on L. Right, and so, well, now the next big observation is that this is not just for this one particular line L, right? I could have just as well have picked maybe another point. Let's say I pick some point X prime, Y prime over here, and maybe I have another line actually use this feature. Maybe I have some other line L prime, which is also parallel, but just kind of a shift of the line L, another line in the same direction, just going through a different point. well, u also has to be constant along this other line too, right? So u is also constant along L prime, although the value of the constant may be different, right? So maybe u is equal to some number, say C1 over here on L prime, and then maybe u is equal to some other number, C2 on L, right? So maybe if I change the line, I get a different value, but the point is that if I stay on one of the fixed lines, the value can't change and my function has to be constant. Right. And so notice that, okay, well, if I can keep shifting these lines down, right? And I can basically cover the whole XY plane with different shifted versions of lines like this, right? So I can, right? So again, this is my XY plane. I can cover it with lots of different lines which are in direction A comma B, right? And so on each of these different lines, maybe the function u has a different value, but I know that if I stay restricted to one of them and just move along one, the function can't change, right? And so, right, so what does this tell us? This tells us basically that you can think of u as being like sort of only depending on the particular line rather than that the point is on with this particular direction, rather than depending on the actual point. So that's kind of maybe a fancier way of looking at this. A more concrete way to look at this, however, is to just, well, let's just write down the equation of these lines, right? So what is it's relatively easy to write down the equation of any given line. So what do these lines look like? Right, so what's the equation of a line with slope b over a, which is, after all, really all we were looking at above, right? All these lines were just different lines with the slope b over a, with possibly different y-intercepts. Right, well, the equation is just y is equal to b over a times x, plus maybe some other constant r, which is the y-intercept. Right, when x is equal to 0, this is the y value, right? So r is a constant. Right, and so what I'm going to do, just to maybe simplify things, we'll see why in a second, I'm going to multiply this equation through by a, right? So this is equivalent to saying that a times y is equal to b times x plus some constant c, where c is r times a, which is also constant. And here it's crucial to point out that c can be anything, any number. And for each number, you get a different line, right? With the same direction, right? So in the direction A comma B. And so I'm just going to do one more bit of algebra. I'm going to rearrange this equation and write it as a times y minus b times x is equal to c. The reason I did this is because now we have all our variables on the left-hand side, and this is just some constant, right? And so the conclusion, right? So the conclusion is that, right, if I pick any such, the problem of picking one such line is exactly equivalent to just changing the value of c, right? If I change the value of c, I'm going to get different lines. And if I let c go to infinity and minus infinity, I'm going to cover the whole plane with different lines. And so my solution is really just going to be a function of the left-hand side. So u only depends on value of ay minus bx, because this value just tells you which line you're on. And then once you're on that line, you know that it has to be the value associated to that line. And so a way of saying this precisely is that u must equal some function of this quantity. So u is equal to some function of ay minus bx, where f is some one variable function. Right, so again, f is some function. Okay, and so this is the quote unquote general formula for solving a first order linear PDE as long as there are constant coefficients. And so the argument that we just kind of outlined can be made rigorous to show that these are the only solutions, right? If you have a solution, it has to be of this form. And so if you're not completely convinced by the argument I just gave, well, what we can do now is actually check that this is a solution. And so this will prove that this at least is one way to solve the problem. And so let's just check, right? And so let's first take the derivative with respect to x of the thing on the right-hand side. So derivative with respect to x of f of ay minus bx. Well, we have to use the chain rule, right? So this is going to be equal to, well, whatever the derivative of f is. So I'll put f prime evaluated at this point. And then I have to multiply this by derivative with respect to x of the inside of the function, which is ay minus bx. And so I get f prime of ay minus bx times negative b, right? And so this shows that this is what ux is equal to, right? The x derivative of u. On the other hand, if I take the derivative with respect to y of the same function, again, using the chain rule, this is going to be equal to f prime at ay minus bx times d dy of ay minus bx. And so this time I'm going to get, well, the left-hand side is uy, and the right-hand side simplifies to f prime of ay minus bx times a, right? And so we'll notice that ux and uy are very similar. They're just different multiples of f prime evaluated at the same point. And I can make them match up by multiplying them by the respective constants. And so in particular, if I multiply ux by a, I get negative ab times f prime evaluated at this point. And if I multiply uy by b, I get the same thing, except positive, right? So this is equal to ab times f prime at the same point. And so then taking these together, I get that since aux is the negative of bui, I get a times ux plus b times ui is equal to 0. And so this is indeed a solution, right? So right. And so what I could have done is really just written down this formula for you and just been like, okay, I'm going to claim this solves the partial differential equation, and then done this calculation, and you would have been convinced that it does. But then if I did that, it wouldn't have given you much insight into like, how do you actually find this formula? Well, the way you find this formula is by doing this kind of geometric analysis up here related to directional derivatives. And so these lines have special names. So these lines are called the characteristic curves. For the solution, right? And so if all the coefficients of the equation are constants, by following this argument that we just did, the characteristic curves are all going to be lines in the same direction. We're going to see an example soon where as soon as we change the problem to variable coefficients, these curves that we use to find the solutions become a little bit more complicated. They're not just lines anymore, right? And so another good way of thinking about this is in terms of level curves. If you remember, for multivariable calculus, remember the level curve is some curve in the plane on which the function has a one fixed constant value as you move along the curve. And so what we did here was really, without really knowing what the function was, we determined what the level curves have to look like, and then we use that information to solve for the function, right? So we sort of like figured out what the level curves had to be, and then from that information derived what the function had to be. Right, and so at this point, after I just said that, you may object, well, we didn't, I mean, what is f, right? So it turns out that f here can be anything, right, as long as it's differentiable. This argument I just did will work for any function, and so any function f, any choice of f will solve the PDE. So you can immediately see that there are infinitely many different solutions, each of which corresponds to a different choice of your function f. Right, so you have infinitely many solutions to the original PDE, AUX plus BUY is equal to 0, each corresponding to different f. Right, and so if you want a more precise solution than just u is equal to this f of ay minus bx, you need to assume more information, right? And so in particular, you need an initial condition. Right, so you need to get more explicit solution. Right, and so let's just drive this point in with an example. And so let's suppose that, let's see. Right, suppose I have the partial differential equation ux is equal to 2/5 times uy, where u is a function of x and y. And suppose that we also know that if y is equal to 0, that my function u has to equal e to the x, right? And so this is what we would call an initial condition. And remember, we saw this in the last lecture, that it has to be a function, not a number, right? In general, the initial conditions for PDEs will be functions. Okay, well, we can now solve this problem and get an actual legitimate answer that's actually like a concrete function using the methods we just saw, right? And so what we can do first is let's just rearrange this PDE to put it into the form we saw above. So ux is equal to 2/5 uy. That's the same thing as saying that 5 times ux minus 2 times uy is equal to 0, right? And then so from before, we already know that u of x comma y has to equal some function f times, what was the formula? The formula was ay minus bx. And so in this case, our a is equal to 5, and b is equal to minus 2. And so we end up with, right, so 5y minus, or minus 2, so we get plus 2x, right? Right, so I'm just double checking the numbers so that I don't confuse people. Right, okay. Right, and so at this point, well, we have extra information for this example because we know that if I set y equals 0, that this is equal to e to the x. But now let me use the above formula. So this is equal to f of 5y plus 2 times 0, which is equal to f of, or sorry, x is, I'm setting y equals 0, not x, excuse me. Right, so this is equal to setting y equals 0. This is f of 0 times 5 plus 2x. And so then this is equal to f of 2x, right? And so if I take these two bits of information together, this tells me that f of 2x has to equal e to the x. And so therefore, what was my function f? Well, my function f has to be e to the x over 2. Okay, and so, right, we're not just interested in the case when y is equal to 0, we're interested in the general case. But now I know what my function f has to be, so let me just now return back to the formula we had originally. Well, if my function is e to the x over 2, this tells me that, well, my u of xy has to equal e to the input divided by 2, right? And the input in this case is 5y plus 2x, right? And so that's the final solution. Right? And so, I mean, you can see that this is not something you would just, unless you got really lucky, you would have just been able to get from guess and checking, right? We had to do all this analysis to arrive at this point. Yeah. Okay, and so that's about it for the constant coefficient case. So this method will always get you the solution, or this formula. So what I want to do now is move on to the variable coefficient case, which is a little bit more involved. And so, right, so remember, what is the variable coefficient case? So now I'm going to allow a and b to be functions of x and y, right? They could depend on x and y in some ways. And so the main example that we're going to look at for this situation, and then, so I'm going to do all the analysis for one specific equation, and then I'll tell you how the method works in general afterwards. Right, so we're going to look at the equation, consider the PDE x times ux plus uy is equal to 0. Right, so in this case, a of xy is equal to the function x, and b of xy is equal to 1. Right, so one of the coefficients is variable, meaning it depends on x, and one of the coefficients is constant, so it depends on, it's just equal to 1. Right, and so what we're going to do is use what we learned from the previous example and try to generalize this technique to work for this more complicated example. And so what was the first thing we did last time? We rewrote this as some kind of directional derivative. So let's try to do that. Right, so I can rewrite it as, well, I have the gradient of u still, right, which is, right, so this is the vector ux of xy, uy of xy, right? And then I'm taking the dot product with some vector, in this case, the vector, well, I'm multiplying ux by x, and I'm multiplying uy by 1, right? And so this is this equation that I just wrote down is describing the same equation. It's just written in this directional derivative form, right? Okay, and so what does this tell us? So this tells us that right, it says the following. So let's say I'm at a particular point, x comma y. So if u moves, let's say, right, so if the point xy moves in the direction x comma 1, we expect the function not to change, or expect u to remain constant, right? And so what's the problem with this? Well, the problem is that the direction changes depending on what x is, right? So imagine I keep moving, I fix a point, I move in this direction. Well, how do I keep moving in that direction? Well, it's now going to depend on where I end up, right? So at each point, you're going to have to sort of adjust the direction you move in if you want to remain constant. And so this is not describing a line anymore. Instead, it's describing maybe some complicated curve, which we have to understand better. So we're not quite at the solution yet. And in particular, it's going to be a little bit harder to find the solution than in the last example. Right, and so to understand this a little bit better, it helps to again look at a picture. Right, and so let's say this is my point, right? So this is the y-axis, this is the x-axis, and let's say this is my point, x comma y. And let's suppose that I move my point along a curve. Right? So suppose x comma y moves along some curve. Let me just call this curve C, and maybe the curve looks something like this. And again, the curve is in the plane. Right, and so, well, at each point, we want x, y to be moving in the direction that we have, right? So this is like the special direction. Right, so let me call this with quote unquote the constant direction, right? Right, and suppose I can find a curve such that when I move my point x, y along this curve, at every single point I'm moving in the direction x comma 1. Right. Well, what is the direction of movement? The direction of movement is the same thing as the velocity. If you ignore how fast it's moving, right? Remember, velocity also has a direction associated with it. And velocity is the same thing as the slope of the curve, right? So this is the direction, and we want the direction to be x comma 1, right? Right, so this is the same thing as the slope. And so then this is the kind of the key point, right? So what we want to do is find a curve that satisfies both of these properties, that satisfies this property, right? So I want to find a curve with slope x over 1 at each point. Right, and so I'm using slope, right? The slope is the same thing as the tangent vector, the slope of the tangent vector. Right, and so how are we going to make this a little bit more precise so that we can actually get a solution? Well, let's say I parameterize the curve as x comma y of x, right? So at each point x, right? Let's say this is my x value. I get some y value, and I want this to stay on the curve, right? And so the slope is then dy dx, right? So it's the change in y over the change in x. And so if I look at so what is the direction we're moving? So the slope of the constant direction is, well, again, you look at the ratio of the y component to the x component, right? So it's 1 over x. Right, so this is change in y over change in x, which is the same thing as like dy over dx, right, in terms of like the calculus notation. And so we would expect then that whatever this curve is, dy dx should be equal to 1 over x, right? Right, so right, and again, when I say dy dx, I mean y is the function that you get when you parameterize and things like this, right? To make this more precise. If you don't want to worry too much about making this like absolutely rigorous, think of this more as like an informal way to derive the formula or the method, and then you can check that the method works. Right. Okay, and while this is a relatively easy ordinary differential equation that we can solve, right? Because remember now y is just a function of x, right? Y is whatever you get by parameterizing the curve. And then on the right-hand side, I have another function of x. And so I really just have to take antiderivatives, right? You don't even need to use any of what you learned in the ODEs classes you've taken, right? So this tells me that, well, if I integrate or take antiderivatives of both sides, this tells me y has to equal antiderivative of this, of 1 over x, And so what is the antiderivative? Well, it's the natural log of, say, the absolute value of x plus some c. And c is a constant. Right, and so if I simplify, ignore the integral, this tells me y is equal to natural log of x plus c, or y minus the natural log of x is equal to c, right? And so what we just showed is that along this curve, the function u remains constant, right? So for any choice of c, right? Right, and so if we go back, so this curve that I drew here, you can think of this as being the y is equal to natural log of x. And as I move my point along this curve, the value of my function u, which solves the PDE, can't change. And again, the reason it can't change is because of this property involving the directional derivative, which says that if I move in this direction at each point, there's no change. But this is exactly the slope of the curve, which is exactly the direction you're moving as you move along the curve, right? Right, and so therefore, just as before, we expect u of xy to be some function of the quantity on the left-hand side, right? So it only depends on y minus ln of x for some one variable function in f. Right, because, well, maybe if I change the value of y minus natural log of x, which corresponds to changing the value of c up here, I may get different curves, and therefore I may get different values of u. But if I only restrict myself to one such curve, the value of u doesn't change, right? So I should only have one fixed value, which is kind of what this is saying in a more precise manner. Right, and so this is our candidate for a solution. And so, well, let's check that this works, right? So let's first take the derivative with respect to x of u. Well, this is the partial derivative with respect to x of this thing, f of y minus natural log of x, right? And so this is equal to f prime of the quantity I have here times the derivative with respect to x of what's inside. So that's going to be minus 1 over x. Right, because derivative of natural log is 1 over x, but there's a minus sign. On the other hand, if I take uy, that's going to be partial derivative with respect to y of f of y minus natural log of x, which is equal to f prime of what's in the parentheses, and then just times 1, right? Because if I use the chain rule and I take derivative of y with respect to y, I just get 1. Well, this tells me then, again, ux and uy almost agree up to this negative 1 over x. So this tells me that if I multiply ux by negative x, well, then I get this is equal to f prime of this quantity, and so that's equal to uy. Right, and so therefore 0 is equal to x times ux plus uy, which is what we wanted to solve, right? Right, so we found the solution. And so once again, if you don't specify more information about your function, this is the only thing you can say, right? So you just know that there's some function f for which u satisfies this formula, you just don't know what it is. If you add in an extra initial condition, you can actually get a complete solution. So for example, suppose x times ux plus uy is equal to 0. And also, for example, what's a good initial condition? So let's say u of 1 comma y is equal to sine of y. right? And so once again, this is my initial condition. Right, and so now that we have this extra bit of information in the blue box, we can get a full solution. So from before, we know that u of x comma y has to equal some function f of y minus natural log of x. For some f. And now what we want to do is use the initial condition to determine what f has to be. So therefore, if I take, right, my initial condition tells me that if I plug in 1 for x and let y be arbitrary, that this has to equal sine of y. But if I use the formula we derived, it also has to equal this function f applied to y minus natural log of 1. Remember that the natural log of 1 is 0, so this is just f of y. And so this tells me that f of y has to equal sine of y. And so now finally I can plug in this function I found out, and so now I have my general solution. So the solution is u of xy is equal to the sine of y minus natural log of absolute value of x. And so once again, this is a solution that you definitely would not have been able to, unless you got lucky, to just kind of guess, right? We had to do this analysis of these curves, finding these curves, right? Right, and so what are the similarities? Well, if I go back to what we saw originally, in the constant coefficient case, we were still finding these kind of special curves on which the solution has to remain constant, except they just happen to be lines, so they're easier to work with. In the variable coefficient case, you can have more complicated curves, right? For example, you can have like a natural log or something like that, or, right? I mean, it's gonna depend on whatever the coefficients are. Right. And as before, these are called like the characteristic curves. Right, these curves that we found by looking at the equation, interpreting it as a directional derivative, and then solving some ODE to like write down the equation of these curves. Right, and so since this method involves finding these things that are called characteristic curves, the method is typically referred to as the method of characteristics. So the analysis we've been doing in these past two longer examples has been something called the method of characteristics. Right. So let me just write this down. Right, and so in this lecture, I'm not going to do any more examples of the variable coefficient case. What I would recommend you do for some practice is look in the textbook. In the textbook, there are a few more examples which are different than the ones I did here, which you can see to get more practice of how to apply this method. And maybe I'll prepare 1 or 2 examples for the Zoom meeting when we discuss the material from this lecture. Okay, and so what I want to just do to finalize this discussion is just talk a little bit more about the general solution method, which is really exactly what we've seen in the past 2 examples. So let's suppose that I know that I have my function u as a solution to the general variable coefficient first order equation of this form, right? So some function a times ux plus some function b times uy is equal to 0. A and b are given. Right, well, how do we solve this? Well, as before, you need the gradient of u dot product a of x y, b of xy equal to 0. And so that means if you move along the direction given by this vector with a and b, your function has to be constant, right? So u is constant along direction a of xy comma b of xy, again using the directional derivative interpretation. Right, so let me write this as bullet points. Well, what does it mean that u is constant along this direction? It means that if I can find curves which have at each point this vector as their slope, then along those curves u has to be constant, right? And so the slope, well, what is the slope? What is the slope of this vector? Well, it's equal to b of xy over a of xy, right? And so this is the same thing as like change in y over change in x, right? So this is like dy dx. And so in order to actually solve for what these curves have to look like, we want to solve an ordinary differential equation, or ODE. Dy dx is equal to b over a. Right, so for example, before we had dy dx was 1 over x. In general, it'll be a little bit more complicated. Right? And so assuming you can solve this ordinary differential equation, which could potentially be a challenging problem, but let's assume you can solve it. Well, then we just argue as before to see that u of xy is equal to some function times the, right? So suppose, like say y of x is the solution. Or let's not say y of x, let's say y is equal to g of x to the ordinary differential equation. Well, then I can write u has to be some function of y minus g of x, right? This could be some constant, which could change, right? And so then this is the general form of the solution for some f. And so the f will be determined by initial conditions. Which would be given to you if like someone wanted you to actually write down a full solution. Right. Okay, and again, it's nice to have this sort of abstract frame, like step-by-step guide to how to solve these PDEs written in your notes, just for reference. In order to actually get used to this method, though, I would recommend first reading a few of the more examples that are in the book, and then doing some practice problems, right? And so your homework has a few problems where you'll practice this method. But at the end of the day, it really boils down to one: can you solve the ODE I have here, which is determined by B and A, which are given to you, and then assuming you can solve that ordinary differential equation, you can get your solution just by using this formula. Right, where G would be the solution to the equation. Right. There. Right, so that gives a pretty complete picture about how to solve first order equations. What we're gonna do starting next week is move on and look specifically at some more complicated second order equations where there's not really necessarily a general method like this available. But before we do that, we're gonna kind of pause the mathematical analysis and instead talk about like some important examples of interesting partial differential equations and in particular how to derive them based on physical principles. And so we're gonna move on now and talk about derivation of some important partial differential equations. And so if you think back to the first lecture, I gave two examples pretty quickly. The first was something called the transport equation, or sorry, the second was something called the transport equation, which describes how some like pollutant in a pipe moves along as the water moves at a certain speed. And then the first example we looked at was a second order equation, which is something called the wave equation, which describes kind of wave-like movement in space. And so the first question that anyone should have when they see these equations is not like how to solve them. The first question you should have is like, why does this describe the motion of a wave, or why does this describe the transport of something moving through a pipe, right? And so these are the questions we're going to address first, just to provide some more intuition and more physical background before we like go too heavy on the mathematical analysis of these equations. And so what we're going to be talking about is material from section 1.3 in the book. We're going to look at two important examples, in particular three. So we're going to look at the transport equation and the wave equation and explain how to derive these. And then there's a third equation, which is equally important, which is called the diffusion equation, which we'll also discuss how to derive. And so if you look in the book, there are other examples of different important PDEs which show up in physics, where the author goes through how to derive them as well. We don't have time to discuss all of these in the lecture, but if you're interested, yeah, I would also recommend reading those. For purposes of like exams and things like this, I would only test you on the methods that we talk about in the lecture, just as a side comment about that. Right, and so I also want to point out that so we're gonna first study the transport equation, then the wave equation, talk about how to derive these from physical principles, and then we're going to talk about something called the diffusion equation, again, how to derive it from physical principles. So my treatment in the lecture of the transport equation and the diffusion equation are going to be basically what's in the textbook. I'm not a big fan of how the book derives the wave equation, so I'm going to give a slightly different derivation, which I think is a little bit more insightful and also teaches you some interesting math along with it. And so the wave equation, I'll do the derivation next lecture, and I'll also do the diffusion equation derivation next lecture. For the final part of today's lecture, we'll talk about the transport equation. Right, so let's. And in fact, it's sort of natural to talk about this equation because if you recall, this is an example of a first order partial differential equation. And in fact, it's an example of the simplest type with constant coefficients. Right, and so what is the transport equation describing again? Just for quick review. Well, let's consider, let's say, water moving in pipe, say to the right, at some speed. Let's say the speed is c. Right, so I have, and let's suppose the pipe is horizontal too. Right, and so I have my direction of movement, which is say the x-axis, and so I have some pipe. Right, and then I have some water that's flowing along, right? Right, and the water is moving at speed c. And suppose that some like foreign object or pollutant or something is placed in the water. Well, then this foreign object we expect to move with the water, right? So the object transfers or transports by the water. Right? And so this is some kind of simple physical system where, again, there's this water moving. I input some pollutant in the water, and we want to understand how that moves with time, or how the concentration changes with time, right? And so what we're going to do is, we're going to define a function, say u of xt, where t is like, say, bigger than or equal to 0, which is evolving, corresponding to the physical system changing. And so I'm going to let this be the concentration of the pollutant at position x. Right, so maybe this is position x over here, and I have a lot of pollutant at that point, and time t. right? So the first variable describes what position in the pipe I'm looking at. The second variable tells me at what time I'm at, like as time evolves, like am I at the first minute, second minute, et cetera, right? Or first second, third second, et cetera. Right, and so what is the transport equation? Well, we're going to claim that U has to be a solution to the following PDE. So the partial differential equation is if I take the partial derivative with respect to t and then add on c times partial derivative with respect to u, this has to equal 0. Where c equals the speed of water, as we saw before, and we're going to assume that it's constant. Let's say it's constant, just to simplify things a little bit. Right, well, this is a first order linear equation. Right, so we know how to solve this PDE already, but I don't want to talk about how to solve it. I want to talk about like why does this equation describe this physical system? Right. Okay, and so that's what we're going to talk about now. So let's make this maybe just like let's label things. So let's say I'm looking at x between 0 and some point b, right? So let's derive the equation. Right. So remember that, like, how are we going to do this? Well, remember that U is the concentration of the pollutant at time t, right? And so I can write my function U of xt, right? Think about it in terms of units, right? So this is like the amount of your pollutant, for example, per centimeter, right? Let's say we're measuring distance in terms of centimeters. You can use any length you want. And so notice that, well, what if I wanted to think about a quantity that's, right? So if you think about the system, you have whatever pollutant you put in the pipe, it's moving along to the right. However, if I fix an interval of a particular length and I let time evolve, well, then everything in that interval is going to move a little bit to the right at a certain speed. But notice that the total amount of stuff that's in the interval you don't expect to change over time, right? Because, right, like the pollutant is not disappearing into thin air or anything. It's just moving to the right and everything's moving at a constant speed, so it's not going to spread out. So you would expect that maybe if you measure the amount of pollutant, this is at least a quantity that doesn't change over time, right? And so we're gonna do this, and then we're gonna use that observation to derive the equation. And so what I'm gonna do is let m denote the amount of pollutant, say in the pipe, between x equals 0 and x equals b, right? And so for us, remember, well, we talked about fixing our domain from like x is equal to 0 to x is equal to b. Well, imagine that that's just a section of the pipe and that the pipe keeps moving, right? So it's going to help maybe up to 2b or something. It's going to help to be able to think about what happens if it moves a little bit further. And so we're going to extend the domain a little bit. And so m is just going to measure, right, how much of the pollutant is between 0 and b, right, at a particular time. Let's say at time, we fix time t. Right, where t is fixed, right? So yeah, let's say this is fixed. Okay, and well, given that my function u, if I at time t, tells me the concentration, how can I derive the total amount, right? So that's a question. Well, notice that, like, let's say I'm in a tiny interval, say between x naught and x naught plus a, where like a bigger than 0 is really small. Right, well then you expect that the concentration at point x naught is probably about the same as the concentration at point x naught plus a, if a is very tiny, right? Because you're only changing it by a little bit, so the concentration is not going to change too much. And so therefore you expect that the total amount in this interval should approximately be equal to u of x naught at t times the length of the interval, which is a, right? Right, so you expect to be able to sort of figure out the amount in a tiny interval by taking the value of the function and multiplying it by the length of the tiny interval. And so if you add up the contribution of all the intervals from 0 to b with this tiny parameter a, that should give you a good approximation of the amount of pollutant that's in the pipe. And the approximation should get better and better as you take the limit and let a go to 0, right? And so the way to make this precise is just to write down an integral, right? So instead of u of x naught t times a, you have u of x comma t times the change, a, remember a here is like the change in x from x naught to x naught plus a, so that's going to be a dx. And you're going to be adding up all these contributions. Remember, integrals are sort of ways of precisely summing in exactly this manner. And so x is ranging from 0 to b. And so we should have m is equal to this integral from 0 to b, right? And so what we're going to do now is let time evolve by a little bit. So let's say t goes to t plus h, where h is very small but positive, right? So I just let the physical system evolve over a very short period of time, right? And so in this period of time, well, maybe this is between 0 and b, right? So this is the portion of the pipe between 0 and b. This is going to move to the right a little bit by some amount, right? And so let's first determine exactly what that amount is. So notice that c is equal to the speed, right? And so speed is like the rate that the position is changing with respect to time, right? So that's going to be the change in x over change in t, right? Well, the change in t is exactly h, right? Because I've perturbed t by this quantity, excuse me, I've perturbed t by this quantity h. So therefore we expect that the change in x should be change in t times c, right? So it should be h times c, right? Because h is the change in t. And so therefore we expect the pollutant between 0 and b, let me have more space to write this. So we expect the pollutant between 0 and b to move to the right by about x, by a change in x of about h times c, right? Right, so I expect the pollutant, let's say this a little bit more precisely, we expect the pollutant that's in the interval, say between 0 and b, to move to the interval, well, I'm changing x by h times c, so it should move to the interval 0 plus hc comma b plus hc, right? So that's just the interval hc comma b plus hc. But the pollutant is just moving to the right, right? So the amount in this interval shouldn't change. Again, it's not like disappearing into thin air, it's just moving, right? So the amount should still be the same. Right, and so if we argue as above, we have a similar formula for the amount in the interval between hc and b plus hc. It's again going to be an integral, but now the domain of the integral is going to go from hc to b plus hc, right? And so therefore, we also must have m is equal to integral now from hc to b plus hc of u. But now we're not at time t, right? I almost made a mistake. We're not at time t. We've perturbed the time by a little bit, right? So we have t plus h instead of t, right? But then we're integrating with respect to x, right? And so, well, now I have two different integrals which are equal to the same quantity. So then these integrals must be equal. So we need to have integral from 0 to b of u of xt dx is equal to integral from hc to b plus hc of u of x comma t plus h dx, right? And so now what do I have? I've shown that two different integrals of my function have to be equal, but I don't want an equation involving integrals. I want an equation involving the original function, u. So how do we get from integrals to the functions that are being integrated? Well, we can use the fundamental theorem of calculus, right, to sort of go from integrals to the function by taking derivatives, right? So what does the fundamental theorem of calculus tell us? If I differentiate the left-hand side with respect to b, well, this just means I plug in b for x, so I get u of bt. And similarly, if I differentiate the right-hand side with respect to b, right, so I'm just going to plug in b plus hc. So I get u of b plus hc comma t plus h, right? And again, right, so why did I do this? Well, I had an equation involving u that has a bunch of integrals, and I don't want integrals. I want an equation involving the function u. And so I can pass from an integral to the function u by taking the derivative and with respect to the parameter b, and then using fundamental theorem of calculus, which is what I just did here. And so therefore, well, what does this tell me? Well, the left-hand side, if I differentiated it with respect to b, I got u of bt. And on the right-hand side, if I differentiated it, I got u of b plus hc, comma t plus h. And so these have to agree for any b, right? And so now notice that I have this extra parameter h, which is floating around, but the left-hand side doesn't depend on h. However, on the right-hand side, h was positive but arbitrary, right? And so this means that the left-hand side is a constant in terms of the function h. So if I take the derivative with respect to h, the left side will be 0, but the right side will be some function involving derivatives of u, right? So now what I'm going to do is differentiate with respect to h. Right, and so left-hand side, if I take derivative with respect to h, I just get 0, right? So using ddh of u of bt is equal to 0 because neither b nor t depend on h. And so that's going to be equal to now derivative with respect to h of u of b plus hc comma t plus h. Well, what do we have here? We have u as a function of two different variables, right? You have the first variable and the second variable, and both of these things I have quantities that depend on h, and I want to take the derivative of the whole thing with respect to h. And so in order to do this, I have to use the multivariable chain rule, right? So what I'm going to do is just write down the solution that you get by applying the chain rule to this function. And if you want some review, what you should do is maybe pause the video and just try to write out this derivative yourself and then check against the answer that I write down. Right? So this is something that you should hopefully be able to do. Right, so if I apply the chain rule, what do I get? Well, I get the derivative of u with respect to x, right? The derivative of the first component evaluated at this point, and then times derivative with respect to x of what I have here, or sorry, derivative with respect to h of what's in the first component. And then I have a second term that I add on, right, which is the derivative with respect to the second component, where say I'm viewing this as like my x component and this is like my t component. Maybe it'll help if I have like t naught instead of t here, if that's a little confusing, right? Right, and so going back to the chain rule, right, so I get u of t at the point, right? So add b plus h. Let me change t to t naught here. T naught plus h. And then I have to multiply by derivative with respect to h of the second component, which is t naught plus h, right? Okay, and so I'm almost done. Let me just write out what these derivatives are. Well, what is the derivative with respect to h of b plus h times c? That's just c. What is derivative with respect to h of t naught plus h? That's just a 1, right? And so this equation tells me then that I need 0 is equal to ux b plus ch t naught plus h plus ut, or sorry, times c. That's important. Plus just derivative with respect to t now, evaluated at the same point. Right? And so this looks like exactly what we want, right? So now let's just gonna set let us just set h equals 0. And let's say we set b equals x and t naught equals t. Well, then we have our equation, right? We get 0 is equal to c times ux plus ut. Right, and so that's exactly the transport equation. Right, and so this is the derivation, right? And so notice we made some basic physical assumptions which have nothing to do with math, right? And so the physical assumptions were that the pollutant is kind of moving to the right at a constant rate and not spreading out too much, so that we can relate these two integrals which measure the amount of pollutant in a certain region. But then once we use those physical principles to get this equation involving integrals, we then use some mathematical analysis to derive the partial differential equation, which describes the motion. And so in the next lecture, we're gonna do something very similar for the wave equation, except the derivation will maybe require like some more ingenuity and will be a little bit more involved and I think a little bit more interesting than this example. It's worth pointing out that we know how to solve this equation, right? So if I give you a particular initial data, we can use the methods that we talked about at the beginning of the lecture to actually solve the transport equation. And so the solution will then presumably give like a nice description of the particular physical system you're looking at involving this transport phenomenon. This is of course going to depend on the choice of the initial condition, which should be physically relevant in some way. And so I'll talk a little bit about this at the beginning of the next lecture as a warm-up before we move on to the wave equation and the diffusion equation.